Thank you. My name is Ran Liu, and I'm from Carnegie Mellon University. And just a little caveat, this presentation is in the Bayesian modeling session, but it has almost nothing to do with Bayesian modeling. So sorry to disappoint any of you who came here for that reason. But I hope you'll still find the talk interesting and perhaps even help me brainstorm some ways that our approach could be incorporated into models like BKT. All right, so as the use of educational technology becomes more and more ubiquitous, the usage data that's logged by such technologies can provide us with a lot of rich data for assessing and understanding students' skills and concepts and mental models and learning trajectories. We can think of these aspects of human intelligence collectively as a knowledge base whose elements are knowledge components. And so Koedinger, Corbett, and Perfetti defined a knowledge component as an acquired unit of cognitive function or structure that can be inferred from performance and relevant tasks. Modeling educational data typically requires something like a knowledge component model, which involves the mapping of these actual knowledge components to tasks or problem steps. This knowledge to task mapping provides a way to convert basically a symbolic cognitive model into a form that can be used by statistical models to make predictions about student performance on these tasks or problem steps. So I'm just going to give you guys a simplified example of something that you might see in a KC model. So the domain that I'm actually going to be talking about today is fraction arithmetic, so the example is from that domain. So these columns you can see are potentially relevant knowledge components to doing fraction arithmetic. And in this first problem step, the student has to multiply 1/2 times 3/4. And so the knowledge component for the procedure for multiplying fractions might get tagged. Similarly, if a student has to add two fractions with different denominators, they have to apply the knowledge component that supports knowing the procedure for that. And in addition, sometimes you'll see that there are additional difficulty factors present. And so there can be multiple knowledge components tagged for a single problem step. In this particular case, in order to execute the correct procedure for adding these fractions, the student has to know how to find the least common denominator and also has to know how to find equivalent fractions once they've determined that least common denominator. So when you couch this kind of KC model within a statistical model, or basically like a mathematical abstraction of the relationship between various features of the learning environment and some kind of observable outcome of learning, you can start to make inferences about student knowledge based on observable behaviors. So for example, if the student gets the multiplication problem correct, then typically a student model will then update its estimate of how much that student knows the procedure for multiplying fractions. And similarly, it would update, well, at least in additive models, it would update its representation of all the knowledge components tagged for this fraction addition problem to improve the likelihood that the student knows those. All right, and if the student gets the multiplication problem wrong, the model typically will decrease the estimate of the student's knowledge of the fraction multiplication procedure in typical models. So the vast majority of educational data mining work has focused on estimating students' positive knowledge components. That is, knowledge components that really can only help performance on relevant tasks or problem steps. So when students make errors, though, as seen in the previous example I just showed you, student models will typically respond by lowering the likelihood that the student has the relevant positive knowledge component. So it is true that sometimes errors reflect a simple lack of knowledge about how to do that kind of problem step. But oftentimes, students make errors that reflect a thoughtful but incorrect strategy. For the purposes of this talk, I'm going to call this sort of class of thoughtful but incorrect concepts or strategies or procedures as misconceptions. So I've talked to some people already about this work, and I guess the term misconception has been used to refer to something more specifically conceptually grounded. So I'm just going to ask you to forgive me for this terminology, and maybe if you have any suggestions about a broader term I could use to capture, like misconceptions, misprocedures, all of those kinds of things. So the goal of this work that I'm about to present is to extend KC modeling to accommodate the representation and the assessment of misconception-like KCs. Okay, so the current state of KC modeling is that any given KC can only be positively mapped to performance on a problem step. So this doesn't really allow for us to model misconceptions as KCs since they lead to negative performance on at least some problem steps. So we propose to extend KC modeling to accommodate misconception-like KCs by mapping them to problem steps on which they could apply, but to use -1 in addition to 1 and 0 coding. So misconception would get coded as a -1 or it would get coded as a 1 for problem steps in which applying it gives you the correct answer, but for the wrong reason. And it would get coded as a -1 anytime it would yield an incorrect answer. And then just as with normal KC modeling, any problem steps on which it applies would just get coded as 0. So I'm going to present to you a case study where we applied this to a particular misconception in fraction arithmetic, and hopefully that will give everyone a more intuitive sense of how we were able to code this misconception into the data, as well as what effect it has on the model. Okay, so the misconception that we focused on in fraction arithmetic is called independent whole number strategy, and it's very commonly seen among students. I guess you could call it more of a misprocedure. But basically in this strategy, students basically just apply the operator that's in the problem to the two numerators to generate the numerator of the solution, and then they apply the same operator to the two denominators to generate the denominator of the solution. So you can see in these examples that when applied to multiplication, students will generally get the problem correct, and when applied to addition, they will generally get the problem incorrect. So this is an example of the tutoring interface that the data set came from. By the way, just a side plug, this tutor was created using cognitive tutor authoring tools, which is something created at CMU that you can really use to create any kind of educational intelligent tutoring system. And so you can see this is a very simple interface. Students get to, in this problem, input just the numerator and the denominator, and they get immediate feedback and can ask for hints and all that good stuff. And similarly, this is an example of the multiplication interface. And then here's an example of addition with two different denominators. And just to note, since you'll want to reference this in later slides, there is this little checkbox that students have to check to indicate that they recognize that in this kind of problem, they have to convert the fractions to have a common denominator before they can proceed. So once they check this checkbox, you can see these additional, sorry, it's a little bit hard to see on the screen, but these additional squares and, well, additional fraction components appear so that it gives the student a way, an intermediate way to convert the fractions first before adding them with a common denominator. Okay, so that's just an example. So this data set is available on PSLC Data Shop. Yeah, I think we uploaded the KC model there as well, so you can access that. I think you have to request permission, but it should be granted. All right, so we started off with an original KC model that was created by not only a domain expert, but also someone who's an expert in studying how students learn fractions. It's my co-author, Rony, created this original KC model. So I'm not going to go into every single detail, but I'll leave it up there for a couple of slides, and you can check it out. Now, the interesting part is kind of how we decided to code the misconception in. So you can imagine that all of the green circles are 1, and all of the red circles are -1. So I'm just using that scheme to show you how we coded it. So you can see here, when you add fractions with the same denominator, adding the numerators is the correct or will generate the correct numerator answer if they're just simply applying this strategy, but adding the denominators is not right. So essentially it predicts that the student would get the numerator right but the denominator wrong. Similarly, for multiplying, they would get both the numerator and denominator correct, so both are coded as ones. And for adding fractions with different denominators, they would not only get this checkbox wrong because they're supposed to check it before they proceed, but they would also get both the numerator and denominator wrong on their first attempts at either. And then once they've sort of progressed past that phase, there's still another opportunity because they're going to have to later add fractions with the same denominator, and they might, again, add the denominators. So there's an example there. All right. So before I show you the modeling results, I'm just going to do a quick overview of the statistical model that we used in conjunction with this misconception KC modeling approach. So we use the additive factors model. It's a logistic regression model that basically models the probability P ij that student I will get a problem J correct based on the student's baseline ability, as well as the baseline ability for all skills required on any given item, the baseline difficulty of each of those skills, or easiness, you can think of it as that, and also a learning rate for each skill that's basically multiplied by the number of opportunities by that item that the student has had to practice that skill. So we worked within this model because there's a lot of precedent for using the additive factors model towards KC model improvement. All right, so I'm not going to go through all of these coefficient estimates, but just to give you a sense, the additive factors model is essentially going to give us an ability estimate for each student. That's the student intercept. And in addition, for each of the normal skills in the KC model I had shown you earlier, it's going to give you a sort of easiness estimate of that skill, and it's going to give you like a learning rate estimate of that skill, and that's what the slope refers to in those. All right, so first what we did was just added simply an additional intercept for this misconception KC. And you can see that right away, so we use AIC and BIC to assess model fit. They're essentially log likelihood with penalty for adding additional parameters. And you can see that the AIC fit, so lower is better in this case. And you can see that the fit improves with the addition of just an intercept for that misconception KC. And the BIC improves as well, and it has harsher penalties for additional parameters, so that's good. And then in addition, you can see that the misconception KC, the coefficient estimate for that intercept, is quite positive and quite statistically significant, suggesting that there is, in fact, a strong presence of this estimated by the model in the data set. And just to kind of give you an intuitive sense of what happens to other KC estimates, as you add something like that misconception in, you can see that the coefficient estimate for the procedure for multiplying has actually decreased, meaning that the fact that students are probably getting some multiplication problems correct just because they're applying this strategy, maybe not because they necessarily know that that's what you're supposed to do for multiplication, will lead it to, lower the estimate for the likelihood that they know the proper procedure for multiplication when they see a multiplication problem. In addition, for something like finding the least common denominator, typically when students do that correctly, it's in the same interface location as where they could potentially apply this strategy and add the denominators instead of waiting to find the least common denominator. And so because the misconception absorbs some of the attribution for that error in that interface element, it thinks that, oh, maybe students actually know how to find the least common denominator better than we thought, but they're just kind of getting derailed by this misconception. All right, so in most cases, regular cases, they also have a learning rate that's modeled in addition to just an intercept. And so when you do opportunity counts, which are the basis of figuring out the learning rate for KCs, it's pretty straightforward. Basically, you say anytime you have an opportunity to apply that knowledge component, that counts as an opportunity. With misconceptions, it's a little bit trickier because, what exactly counts as an opportunity to increase or decrease that misconception, right? So the way that we did it here was we actually had two different opportunity counts, so two different rate parameters. One of them is for opportunities to sort of proliferate that misconception, like make it worse. And those are opportunities like multiplying, where you might apply it and then get the answer right and think, oh, this is good, this is something that might get strengthened. Whereas cases where you apply it, such as in the add fractions with different denominators, you would get immediate negative feedback, and you would realize you had done something wrong and have an opportunity to basically unlearn that misconception. So again, we basically counted all these red circles as opportunities to unlearn the misconception and the green circles as opportunities to proliferate it. Okay, so if we add in the opportunity-weighted aspects of the misconception KC, you can see that it further improves the fit of the model to data. And interestingly, you can see that it lowers the initial estimate, like the intercept estimate for the misconception, but has some interesting and significant, it shows some interesting significant effects of the opportunities to proliferate it or unlearn it. So in particular, you can see that opportunities to increase it is positively weighted towards that misconception KC, and opportunities to unlearn that is negatively weighted. And what's kind of interesting is that the magnitude of the effect of opportunities to unlearn it is actually a bit greater than the magnitude of effect, the magnitude of the estimate of opportunities to increase it. I think, well, I don't want to read too much into it, but that's good because we want kids overall to be unlearning the misconceptions that they have within the data set. All right, so one of the things that you might be wondering is, and that, for example, teachers might be very interested in is, can we get individualized estimates for this particular misconception KC to kind of see which students might be particularly at risk for it? So what we did was extended the model to have an additional separate intercept for each student. And we found that taking those parameter estimates for each student, we were able to validate them on external data from each of those students. So we looked at the pre-tests and actually coded all of the errors on the pre-test that were indicative of the independent whole number strategy. And there's a quantity for that for each student, and those are significantly correlated with the model's estimate of that student's activation of that misconception within the data set. So this is an example of also validating this approach on something external to the process data on which we developed the model. Okay, so just to summarize, we increased the flexibility of KC models to accommodate misconception-like KCs, and this is quite general. It could be anything that essentially would systematically predict incorrect performance on certain problem steps. And we use this method to model a common misconception in fraction arithmetic, which then improved the student model's predictive accuracy when fit to data. It also yielded interpretable estimates of both knowledge and learning, which I gave you guys some examples of. And they were informative, especially I thought the weights for the opportunities to proliferate and unlearn the misconception within the data set. And also generated externally valid estimates at the individual student level of learning and knowledge. And one of the ways in which I think that being able to incorporate something like a misconception like KC into a KC model is that it changes the dynamics, as we saw in the example, of success and error attribution by the student model. And I think that if incorporating something like that improves the accuracy with which the model can attribute knowledge on other positive KCs, I think that that's good for our use of learning analytics to understand student knowledge. So some future challenges, and if anybody has any thoughts about this, I would love to chat about it. There's some things I've been thinking about. We basically did, as a proof of concept, one misconception KC and really focused in on interpreting and understanding what happens when you add that. But in reality, within any domain, there's going to be multiple misconceptions, and sometimes they might apply to even the same problems. One of the caveats is that, as is with a problem for any kind of multi-KC model, if you have too many multi-KC steps, and especially if you start tagging problem steps with positive KCs and multiple misconception KCs, you can really easily run into a determinability problem in terms of fitting the model and making those attributions. So it's important to remember that KCs really need to predict unique patterns of performance across problem steps. So you need to have a fine-grained enough kind of problem step breakdown to be able to discriminate among sources of knowledge attribution, and you need a lot of data. And also, I think it would be really good to think about how we can start to incorporate explicit representations of misconception like KCs into the outer loop of intelligent tutors, for example, BKT or PFA, that could actually drive intelligent tutoring live, so that we can improve the knowledge attribution of those adaptive engines as they're running. I know that within our department, there have been some new efforts to create better dashboards for teachers. And in interviews with teachers, they've expressed especially that they're interested in knowing about misconceptions and which misconceptions are strongest in their class overall, as well as for specific students. So I think that it would be a really great way to incorporate some of the results of these models into teacher-friendly dashboards. All right, thanks. Take any questions if you guys have.
All right, questions.
All right, so my question is, did you conduct an LR test between the models to test whether or not there was a significant difference between?
Yes, and it is significant, yeah. It's in the details are in the paper.
So, hi, nice work, and I apologize if I missed something, but did you do analysis of learning and forgetting of the misconceptions? So some kind of learning curve or the PK learn. So do you know how this misconception changes with attempts? And
yeah, so well, we have the learning and the or like the proliferating and the unlearning estimates, right? So those are slope estimates that suggest, overall that students are, or do you mean at the individual student level? Is that what you're asking?
I kind of mean to see an interaction between the correct rule and the misconception.
An interaction between the correct rule and,
The more proficient I become in what I should be doing, the more I forget what I should not be doing.
Yeah, so I think that the fact that overall, if you look at the increase and the decrease coefficients for the misconception, it suggests that overall they're applying it less, right? So we know that, but I'm not sure that we can infer directly from this model anyway that they're doing it because of their increases in other knowledge components. I mean, we can look at things like as they do certain problem types more, right, they get better. But that's essentially what we're doing by estimating, like, okay, add different problems, they're getting negative feedback, and that should cause them to, right? So that's essentially, we're already looking at how experience getting feedback on different problem types activates or decreases the misconception. But I think it would be difficult to assess the direct relationship between other knowledge components in the model and that, yeah. But
So, nice talk. I'm trying to figure out, well, first a comment, which is actually, you would never get any of this if actually the sequence of problems didn't actually have adding and multiplying mixed together, right? If they were all
that's
adding
right, yeah,
and
I did.
all multiplying.
Right,
And so,
yeah, they were all interleaved,
right.
yeah.
And so this type of modeling approach, which is kind of neat, it probably actually demands even more attention to the sequence by which the problems are given out. Because oftentimes we talk about KC models and we kind of ignore the data set. We're just kind of saying these are properties of the problem.
Absolutely.
These are really now, this type of bug is really a property of, particular property of the sequence, which makes me wonder, well, I think it's kind of cute and there's something cute about it in that actually you don't even have to know what they typed, right? You're inferring all of this from the sequence of correct and incorrects across problems.
That's right, yeah.
There's something sweet about that, but how far will this generalize? Like, are there many instances, like, have you thought about, is this going to help solve many problems, or is this kind of just like, is this kind of a trick that kind of works here, but I'm just trying to see when would this generalize to?
Yeah, so it's a really good point because, as I mentioned at the end, it does require, if you're just using correct and incorrect information, it does require like a unique pattern of that across problem steps in order to be able to model this well, right? And so I guess what you're asking is, in how many real data sets could you identify a misconception in that unique way? And I think that it is a challenge, but I think one of the things that we should think about doing is moving beyond just correct and incorrect patterns. We can also, potentially extend this. I mean, it would require qualitative change in the method, but we could extend it to actually do attribution using the types of answers that students gave. And that would make it a lot more widely applicable, I think.
Hi.
Hi.
This is great stuff. Question is, when so you've come up with a very clever way of incorporating additional parameters into the model, and you're looking at the parameter estimates as well as their standard errors, and you're saying, okay, well, this is significantly different from 0. Fair enough, right? But and that's all that we ever do with these kinds of methods, whether in AFM or in other models. We tweak them with additional parameters, and we see whether we do better. But isn't there some value in saying, how does this compare against a different class of models, right? So you're tweaking AFM, and we know that AFM is not the shiniest, greatest thing. PFA, for instance, does better for some purposes. What if PFA just does much better than any of the misconception-enhanced models? What do we conclude from that point, and have you done that kind of comparison?
So I think that the purpose of this work that I presented is not actually to make a great fitting model. I think the purpose is to qualitatively change the type of knowledge that we're able to represent in it's really actually more focused in the KC model than the statistical model. It's to sort of extend, what we can represent in a KC model. I mean, this method works in AFM, but it really wasn't meant to compare across models or even optimize models, right? And I wouldn't really call it either a parameter tweak because it's really actually just changing what's within the KC model itself. And I did show the improvement because, you want to know that adding this knowledge component relative to not having it makes the model fit better, suggesting that the knowledge attribution has improved. That's what the improvement in AIC and BIC suggests to me. So I guess my answer to your question is I think that optimizing statistical models is a valuable pursuit in and of itself, but that's not really the focus of this work.
I totally agree with that perspective. The question is whether you could try to incorporate that kind of addition of misconception information in a model that is better positioned to deliver statistically accurate predictions.
Yeah, I think that there are some, I mean, that's one of the future challenges that I posed. I think that there are some potential ways. It's a little bit tricky because you can't immediately adopt the 1, -1 type mathematical outcome in something like BKT, for example. So it's not quite completely trivial to just transfer it from AFM to BKT, but I think it's a very worthy pursuit.
Yeah. Hi.
Yeah.
I don't have any, this is really interesting work and I don't have any questions related to your work. I just have 2 points which will probably add to the list of your challenges.
Mm-hmm.
So a lot of research on misconceptions and common errors that students have show that some misconceptions get solved naturally as students progress to higher grades. So how do we take that into account and give weights to those misconceptions? Again, a lot of research on misconceptions show that not all misconceptions or common errors are bad to have. Some misconceptions are good to have and help in learning the concepts. So how do we give weights to those good to have misconceptions?
So I think that it's a really good point that, you know, students can proliferate this across the grades, and I think that the people who know best are the people who teach them, and I think, and as well as domain experts and people who study the science of that domain, learning in that domain. So I think that it's a really good idea to use kind of theory-driven ways, or at least domain-driven ways of identifying them for modeling. I think that would, you know, help us focus the estimation of knowledge attribution on the things that are most likely, as known by teachers or by people who study that domain, to be big problems. And that's sort of what we did here with fractions. We used kind of a domain-driven way of selecting the misconception. And I think this could be really useful as long as people identify that as something that's likely to be an issue for the students. Yeah.
Thanks, Ryan. Great work. So I have 2 questions that relate to the previous 2 questions, actually. So first, in terms of kind of what the motivation of this was, I just want to comment that, you know, we have these models that have been studied, and it totally makes sense to improve the accuracy of the inferences that we can draw from them, right? And if we are to use data to take action or learn something about learning, we need to make sure that those models are valid and that we've teased apart confounds. So you teased apart the confound of, are they actually learning here, or are they just reapplying, reinforcing a misconception? And that's kind of a self-serving comment too, because tomorrow I'm presenting work on learning attribution improvement with BKT. So
Oh, cool.
So then the other comment of, well, some misconceptions might be useful in that there might be a kind of scenic route that a student can take, right? Kind of productive struggle route that will involve, you know, seeing the boundaries of knowledge, which includes traversing misconceptions. And so I have a technical question related to that, which is the operationalization of this misconception modeling, which is, I couldn't tell from your model if you're actually diagnosing the misconceptions. Like, do they occupy a separate theta per student?
Yes.
They do. Okay.
They do in the last version of the model that I presented, yeah.
Okay, great.
And those are actually related to, so even though those are based on patterns of just correctness and incorrectness, they're related to actual student answers in their pretest that are evidence of applying that, right? So like actually saying 3/4 plus 3/5 equals 6. I forgot the numbers I already generated already. 9ths, yeah, right. 6/9.
This is a really clean application of this in which to demonstrate the power. I want to get your reaction about a conjecture about how this looks going forward in more general applications of this key idea, which is that you're going to, we would try to do this, we're going to run in general settings into 2 very pervasive statistical problems. One is that students that get the things right are going to be, the positive knowledge concepts are going to be relatively homogeneous, but in many settings, and I think this one is special in the misconception being so clear, the number of misconceptions are going to be all over the place, and they're going to apply to very small subsets of students. That's going to make fitting the models hard. The other thing is that, as you know, multicollinearity is the enemy here. And a lot of the knowledge skills variables are going to be negatively correlated with the positive skill variables. So that's going to make using this in general very hard. So how do you get around it? And that's what I wanted to get your, if this is the way you guys are thinking about it. How do you get around it is that you may have to find, to really make this to work, diagnostic questions that are really designed to get around these statistical problems. And intuitively, I think what that's going to end up looking is whenever a student gets it right, you don't worry about trying to fit mistakes, but whenever they start getting it consistently wrong, then you want to understand what class of mistakes they may be doing.
Yeah.
And then what you need to do is deploy these specifically designed questions that are cleverly designed to be able to teach what is it that they are not understanding, what is their misconception. Now, the question then is, if you go that route, which sounds the natural one, do you really need to model the misconceptions, or in your statistical models, can you use indicator variables of how they perform in the questioning test? So in some sense, at the end of the day, to really apply this generally, everything boils down to designing the right misconception diagnostic test, and your variables are just performance in those tests that you deploy when the students are not getting things right.
Yeah, I think that's a really good point. To address your first point, yeah, I think that, as I mentioned earlier, the only way to get around this multicollinearity, or at least alleviate the multicollinearity problem, which I agree with you is a big one here, is to make sure that the various KCs you have really predict unique patterns across the items of data that you have. And as Neil mentioned, that might not be easy in all kinds of domain data sets. I think that one thing that we should do is move beyond, as I mentioned, the 1-0 correctness coding in terms of attribution. We should start using actual student responses for that. It does make a lot of current modeling techniques very tricky to adapt to that, but I think it's a really important goal, because I think that is something that will allow us to get around the determinability problem, right? And then also, I think you make a really good point that you could actually, this is not just in a good solution for misconceptions, but for error attribution or success attribution in general, right? If you really don't know how to attribute some particular piece of performance, you could target questions to figuring that out. And that's very interesting. I would like to talk about it more.
All right. If I see no other questions, I'd like you to thank all three of the last sets of speakers.